Okay, so imagine you are miles from a wildfire, feeling safe. You're behind a highway or a river, maybe even a canyon. Like, that's stop it, right?
It should, right.
But then flames just erupt on your side, out of nowhere. How is that even possible? What if I told you there are equations out there powerful enough to predict a wildfire's every move, anticipating when flames could kind of explode into the treetops? Sounds like science fiction. But you've sent over some research, and it suggests that this is not only possible, but it's happening right now. Today's deep dive is into the top 5 wildfire equations
Okay.
that are helping researchers and firefighters understand these incredible events.
You're absolutely right.
Yeah.
These equations are revolutionizing how we approach wildfires, blending physics and chemistry and real-world observations all into these incredible tools.
So let's jump right in. You've provided me with some incredible resources on this.
Great.
But I have to admit, some of these equations look seriously intimidating.
I can imagine.
My brain is already starting to smoke just looking at them. But don't worry, we're going to break down the key takeaways of each one.
Okay.
We'll uncover how they work and why they matter. Whether you're concerned about wildfires in your area, fascinated by the science, or just curious about the math behind nature's fury.
That's the beauty of these equations.
Yeah.
They can seem complex on the surface, but the insights they unlock are incredibly valuable.
Okay, let's start with equation number 5.
Very.
Albini's spotting distance equation.
Okay.
This one was developed back in 1976, and it tackles those terrifying wind-blown embers that can spark new fires far from the main fire line.
Right.
I mean, it's mind-boggling to think that a tiny ember could travel miles and cause so much destruction.
It really is, and before Albini's work, spotting was often seen as a random, unpredictable phenomenon.
Oh, wow.
Firefighters knew it happened, but they didn't have a reliable way to anticipate it.
So before this equation, firefighters were basically fighting blind when it came to spotting.
Essentially, yes. They relied mostly on anecdotal evidence and gut feeling, but Albini changed that. He brought science to the problem, combining empirical data with principles of fluid mechanics. His equation considers factors like ember size and shape, how they burn, wind speed, and direction, all of which influence how far an ember can travel.
So instead of guessing, firefighters could actually calculate the potential threat of spotting.
Yes.
That must have been a game changer.
Absolutely. Albini's equation dramatically shifted how firefighters approached containment. It made it clear that focusing solely on the main fire line wasn't enough.
Right.
They had to account for those wind-blown embers and the threat they posed to areas far beyond the fire's immediate perimeter.
It's like realizing you've been playing chess with only half the pieces.
Yeah.
Suddenly you see the whole board and the potential moves your opponent might make.
Exactly.
But what I find really fascinating is that Albini's equation highlights the interconnectedness of wildfires and the surrounding landscape.
That's a great point. It's not just about the fire itself. It's about the wind, the terrain, and even the types of vegetation that can carry those embers far and wide.
It's like a chain reaction with each element influencing the next.
Okay, we've seen how spotting can create chaos far from the main fire.
Right.
But now I want to know what's happening inside that swirling inferno.
Okay.
For that, we turn to equation number 4, which is actually less of a single equation and more of a system. The Navier-Stokes equations.
Yeah, these equations are the powerhouses in the world of physics and engineering.
Okay.
They describe how fluids move and interact, and when applied to wildfires, they form the basis of computational fluid dynamics, or CFD models.
Okay, CFD.
Right.
That sounds pretty high-tech. So instead of just tracking individual embers, we're now looking at the entire fire as a fluid with its own complex dynamic.
Exactly. Think of a wildfire as this living, breathing entity
Oh, wow.
with swirling flames, towering smoke plumes, and intense wind currents all interacting in a complex dance.
Yeah. The Navier-Stokes equations help us capture this intricate ballet. They allow us to create incredibly detailed simulations of how the fire might behave, taking into account factors like terrain wind patterns and even the fire's own impact on the surrounding atmosphere.
So we're not just looking at the fire, we're
Right.
looking at how the fire creates its own weather patterns.
Precisely. It's a remarkable example of how a seemingly simple set of equations can unlock a world of complexity.
I bet those simulations are incredible to watch.
Oh, yeah.
But with all that detail, I'm guessing there's a catch, right?
It is. As you might imagine, these simulations require immense computing power and can take a long time to run, sometimes days or even weeks, to model a realistic wildfire scenario.
Oh, wow.
This makes them less useful for real-time decision-making on the fire ground.
So it's like having this amazing high-definition map of the wildfire, but by the time it renders, The fire's already moved on.
That's a great analogy. But even though they're not always practical for on-the-ground operations, the Navier-Stokes equations and CFD models are invaluable for research and long-term planning. They allow scientists to study fundamental fire behavior tests, different firefighting techniques, and better understand how these events unfold on a large scale.
Okay, so we've gone from the unpredictable flight of embers to the intricate world of fluid dynamics,
Right.
uncovering incredible detail about wildfire behavior.
Yeah.
But sometimes we need a simpler, more direct way to predict how a fire might spread across the landscape, especially during large-scale events.
Right.
And that brings us to equation number 3, reaction-diffusion models.
These models offer a different perspective on fire spread, treating it like a wave.
Oh, okay.
They consider how heat from the burning fuel ignites nearby fuel, pushing the fire front forward across the landscape.
So it's like a domino effect, one piece of fuel igniting the next.
Exactly. And these models can be surprisingly accurate in predicting the general movement of a fire front, especially in those large-scale events. But what's even more fascinating is that they reveal how fires under the right conditions can form surprisingly regular shapes. We're talking about ellipses, and even those infinitely repeating patterns known as fractals.
Wait, fractals? Those mind-bending patterns you see in nature, like snowflakes, coastlines.
Yes. It's a reminder that even in the chaos of a wildfire, there can be underlying patterns in order.
Wow.
Driven by the physics of heat transfer and fuel consumption.
That's incredible. But I'm guessing the real world doesn't always conform to those perfect shapes.
Of course not. Real-world factors like wind terrain and variations in fuel type and density all come into play, making things much messier than a simple wave-like model might suggest.
So these reaction-diffusion models give us a good framework for understanding fire spread, but they're not the whole story.
Exactly. They provide a foundation but require careful interpretation and adjustments based on real-world conditions.
That makes sense. It's all about using the right tool for the job.
Yeah.
Okay, we've covered the horizontal movement of wildfires.
Right.
But what happens when a fire leaps into the treetops?
Oh, yeah.
That's got to be one of the most terrifying scenarios, right?
Absolutely. And that's where equation number 2 comes in.
Okay.
We're talking about crown fire initiation models, specifically the work of Canadian researcher C.E. Van Wagner.
Okay, I'm all ears. Van Wagner's work seems crucial because once a fire hits those treetops, things escalate quickly.
Absolutely.
How does his model help us understand when that dangerous transition might occur?
Van Wagner's model focuses on a critical threshold, the intensity of the surface fire.
Okay.
If that intensity is high enough, meaning the fire is burning hot and fast enough, it's likely to ignite the canopy, leading to what we call a crown fire.
So it's like there's this tipping point where the fire goes from a ground fire to a raging inferno in the treetops, and Van Wagner's model helps us predict that transition.
Precisely. And predicting that transition is crucial because crown fires are much harder to control and incredibly destructive.
I can imagine. And that transition has to be terrifying to witness.
Yeah.
1 minute, a fire is creeping along the forest floor, and the next, it's exploding through the canopy.
It's a dramatic shift in fire behavior.
Yeah.
And that shift is largely driven by fuel availability. Think about it. On the ground, you've got grasses, shrubs, and small trees.
Right.
But once the fire reaches the canopy, it has access to this continuous layer of fuel.
Yeah.
Leaves, branches, and tree crowns all ready to burn.
It's like adding fuel to the fire, literally.
Yeah.
And that increased fuel means faster spread, greater heat output, and a much higher risk of spotting.
You got it. And Van Wagner's work has had a huge impact on how we manage forests. His equation highlighted the need for strategies like thinning and controlled burns to reduce the risk of catastrophic crown fires.
Right.
By understanding the conditions that lead to these intense fires, we can take steps to mitigating those risks.
So Van Wagner's equation gives us a powerful tool for assessing the risk of a crown fire.
Yes.
But before we can even apply his model, we need to know how intensely that initial surface fire is burning right.
You're absolutely right. That's where the king of wildfire equations comes in.
Okay, bring on the king.
The one that underpins so much of our understanding and prediction of wildfire behavior. Rothermel's rate of spread equation?
Rothermel's equation sounds like the bedrock of wildfire science.
It really is.
Yeah.
Developed back in 1972 by Richard C. Rothermel.
Okay.
This equation combines empirical data from controlled burns with principles of physics to estimate how fast a fire will spread on the ground, considering crucial factors like wind terrain and fuel type.
So it's like the Rosetta Stone of wildfires, helping us decipher their behavior? by bringing together all these different elements.
Mhm.
But I have a feeling there's much more to this equation than meets the eye.
There is, and that's what we'll delve into when we continue our deep dive in part 2.
All right, we're back and ready to continue our exploration of these incredible wildfire equations.
Okay.
We left off with the king. Rothermel's rate of spread equation, which helps us predict how fast a fire will spread on the ground.
Right.
But you're about to tell me there's more to it than meets the eye.
Yeah.
What makes this equation so special?
Well, it's the equation's elegant simplicity combined with its remarkable power. It manages to distill all the complexities of wildfire behavior, the physics, the chemistry, the environmental factors, all into a formula that's surprisingly straightforward to use.
So it's not about solving complicated differential equations in the field.
Not at all. It's about giving firefighters and researchers a practical tool, something they can use to get a quick, reliable estimate of a fire's potential speed and direction.
Okay, so let's say I'm a fire manager on the ground facing a new wildfire.
Okay.
What information do I need to feed into Rothermel's equation to get those crucial predictions?
You'd start by gathering data on the environmental conditions.
Okay.
Wind speed and direction are key, as is the slope of the terrain.
Mm-hmm.
But perhaps the most critical factor is the type and condition of the fuel.
That makes sense. A fire's going to rip through dry brush much faster than it would through a damp forest.
Exactly. Fuel moisture content is a major player in determining fire behavior.
Yeah.
And that's where those fuel models we touched on earlier come into play.
Ah, yes. Those standardized descriptions of different vegetation types that affect fire behavior.
Precisely. You would select the appropriate fuel model based on the vegetation in your area,
Right.
and that model provides specific parameters to plug into Rothermel's equation.
So it's like having a cheat sheet for different ecosystems and how easily they might burn.
That's a good way to think about it. It takes a lot of the guesswork out of predicting fire behavior.
Okay, so I got my fuel model, weather, data, and terrain information.
Yeah.
I plug all that into Rothermel's equation and...
Out pops your estimated rate of spread. It might tell you the fire is expected to advance at 100 meters per hour, 500 meters per hour, or even faster depending on the conditions.
And that information is absolutely vital for a fire manager.
Without a doubt. Knowing the speed and direction of the fire is essential for making strategic decisions about where to establish fire lines, where to position firefighters, and when to order evacuations.
It's literally life-saving information.
Yes.
But I know no model is perfect, especially when dealing with something as unpredictable as a wildfire.
Right.
What are some limitations of Rothermel's equation?
One of the main criticisms is that it assumes fairly idealized conditions, things like uniform fuel beds, steady-state burning, and consistent weather patterns. But out in the real world, wildfires rarely encounter such perfect scenarios.
So a sudden gust of wind or a patch of bone-dry fuel could easily throw off the prediction.
Absolutely. Wildfires are dynamic and chaotic.
Right.
Those sudden changes can be difficult to account for in any model, no matter how sophisticated it is.
So how do firefighters deal with those limitations? Are they constantly having to adjust their strategies on the fly?
To some extent, yes. Firefighters are trained to be adaptable, to constantly assess and reassess the situation as it evolves.
Yeah.
But what's fascinating is that researchers haven't just accepted those limitations.
Yeah.
They've been working for decades to refine and improve Rothermel's equation,
Oh, yeah.
trying to make it even more robust and accurate in the face of real-world complexity.
So they're essentially future-proofing the equation, trying to anticipate the curveballs that wildfires might throw their way.
Exactly. It's a testament to the power of Rothermel's original work that it's been able to accommodate these improvements and updates.
It's like starting with a solid blueprint and then constantly tweaking and refining it as you gain more knowledge and experience.
That's a great analogy. We've seen the development of more detailed fuel models that incorporate things like canopy density, and the presence of ladder fuels those low-hanging branches that allow fire to climb easily into the trees.
All right.
And we've seen efforts to integrate Rothermel's equation with other models like those that predict spotting or crown fire initiation.
So instead of treating these equations as isolated entities, researchers are weaving them together to create a more holistic picture of wildfire behavior.
Precisely. It's a remarkable story of scientific collaboration and innovation. Rothermel provided the foundation, and then the entire field of wildfire science came together to build upon it, creating a powerful toolkit for predicting and managing these events.
It's amazing to think how much progress has been made since Rothermel first developed his equation back in 1972.
It really is. And that progress is continuing today,
Yeah.
driven by the urgency of understanding and mitigating the growing threat of wildfires in a changing world.
Speaking of mitigating threats, we've talked about how far embers can travel and how fast a fire might spread.
Right.
But what about the likelihood of those embers actually igniting a new fire when they land? That seems like a pretty crucial piece of the puzzle.
You're absolutely right. It's one thing to know an ember can travel a certain distance,
Yeah.
but quite another to know whether it will actually spark a new blaze when it gets there. That brings us to our final equation,
Okay.
the one that ties everything together.
Right.
It's called the probability of ignition equation.
Okay, this is what I've been waiting for. The
Oh.
equation that tells us whether those flying embers are going to turn into full-blown wildfires.
Yeah.
What factors does this equation consider?
Fuel moisture, as we've discussed, is a big one.
Okay.
The drier the fuel, the more likely it is to ignite, but it also considers the size and temperature of the ember, the wind speed, and even the type of vegetation in the area where the ember might land.
So a smoldering pine needle is less likely to ignite a fire than a chunk of burning bark.
Exactly. And researchers have developed detailed models that describe how different types of embers behave, taking into account their size, shape, density, and how they burn.
So by combining those ember models with information about the fuel, the weather, and the terrain, we can estimate the probability of ignition.
Precisely.
Yeah.
And that probability is often expressed as a percentage. For example, a 20% chance of ignition or a 70% chance of ignition. It gives firefighters and land managers a way to assess the risk and make informed decisions about how to manage that risk. It's like a weather forecast for wildfire spotting.
Yeah.
Instead of predicting rain or shine, we're predicting the likelihood of new ignitions.
That's a great way to put it. And just like with weather forecasting, we can't predict wildfire behavior with 100% accuracy. But these models and equations give us a powerful set of tools for understanding the risks and making the best possible decisions to protect lives, property, and our precious natural resources.
We're back for the final part of our deep dive into the top 5 wildfire equations, and we've covered a lot of ground,
Yeah.
from the physics of ember flight to the complexities of fire spread. But what's really stuck with me is this idea of the probability of ignition equation, this
Wow.
weather forecast for wildfire spotting that you mentioned.
Yeah.
It seems like such a crucial tool for understanding and managing risk, especially in a world where wildfires are becoming more frequent and intense.
It is crucial, and it highlights a shift in how we think about wildfire behavior. It's not just about saying this will happen or that won't happen.
Right. It's about understanding the factors that influence those outcomes, the probabilities involved, and then using that knowledge to make more informed decisions.
So instead of dealing with absolutes,
Mm-hmm.
it's more about managing risk. Like we can't prevent every ember from landing in a dry patch of grass,
Right.
but we can try to minimize the chances of that happening.
Exactly. It's about understanding the odds and playing them in our favor. We know that certain factors like dry fuel and strong winds increase the probability of ignition. Therefore, we can focus our efforts on mitigating those risks through things like fuel management, defensible space creation, and even community preparedness efforts.
That makes a lot of sense. It's like a multi-layered approach to wildfire management.
Yeah.
We're not just fighting fires when they start. We're trying to create a landscape and a community that are more resilient to wildfire in the first place.
Precisely. It's about recognizing the interconnectedness of all these factors, the fuel, the weather, the topography, and even human behavior, and taking steps to reduce risk at every level.
This is all fascinating, but I'm still curious about how the probability of ignition equation actually works on a practical level. Let's say I'm a firefighter out in the field.
Okay.
What kind of information am I plugging into this equation to assess the risk?
Well, as we've discussed, fuel moisture is a key ingredient. The drier the fuel, the higher the probability of ignition. But you also need information about the ember itself, its size, its temperature, and how it's burning. A smoldering pine needle, for example, poses a much lower risk than a large wind-blown ember from a burning tree crown.
So each ember has its own personality, so to speak.
Yeah.
Its own likelihood of causing trouble.
You could say that, and that's why researchers have developed these incredibly detailed models that describe the behavior of different types of embers. They consider factors like size, shape, density, and how readily they burn, giving us a more nuanced understanding of their potential to ignite a new fire.
So I'm adding you take those ember models, combine them with information about the fuel conditions on the ground, things like how dry the grass is or how dense the underbrush is, and then factor in the weather, particularly the wind speed and direction.
You've got it. It's like piecing together a puzzle, considering all these different variables to get a sense of the overall risk. And the output of the equation, that probability of ignition,
Right.
might be expressed as a percentage. For example, a 20% chance of ignition or a 70% chance of ignition.
And those percentages give firefighters a much better way to prioritize their efforts, right?
Yeah.
If the probability of ignition is low, they might focus on other tasks. But if the probability is high, they know they need to be extra vigilant about spotting and take proactive steps to prevent new ignitions.
Exactly. It allows for a more strategic and targeted approach to wildfire management.
It's amazing how these equations have taken something as seemingly chaotic and unpredictable as a wildfire and given us tools to understand and manage the risks. I feel like we've gained such a valuable insight into the science behind these events.
Me too. And I think the key takeaway here is that wildfire science is always pushing forward, seeking to refine our models, gather more data, and develop new technologies to help us stay ahead of the curve.
It's a reminder that even in the face of these powerful and sometimes destructive forces of nature, we're not powerless. We have the ability to learn, adapt, and use our knowledge to create a safer and more resilient world.
I couldn't agree more. It's about harnessing the power of science and collaboration to find solutions and build a more sustainable future.
This has been a truly insightful deep dive. Thank you so much for sharing your expertise with us.
It's been my pleasure.
And to our listeners, keep exploring, stay curious, and join us next time for another fascinating deep dive.